Alright, my name is Robbie Netsky, and I'll be walking through my project on transfer learning for tumor identification. So as an introduction, magnetic resonance imaging is crucial to many medical diagnoses. MRI uses a magnetic field and a computer-generated radio waves to create images of the organs and the tissues within the body. Some examples of applications for this are identifying aneurysms, spinal cord disorders, and tumors. So here's an example of what an MRI scan might look like. This is a pretty high quality one. So given a set of labeled MRI scans, I decided to use transfer learning to identify if there's a tumor present in a scan. So moving on to the methodology here, I utilized a data set that can be found on Kaggle. It includes 253 brain scans. 155 of those do not show a tumor, while 98 do have a tumor present. So the data is pretty balanced between classes, which was good. But there is very limited data, so on top of rescaling the RGB values to take a 0, 1 value in each image tensor, I also introduced random augmentations through the Keras image data generator function, which allows you to augment the images as we went over in homework 4. So by introducing these novel changes, the hope is that we can avoid overfitting to these very limited amount of images and hopefully build a more robust model. So we'll go ahead and begin describing the simple model. After I pre-process the data described before, we're ready to build one. So I began with just a baseline model that deploys a standard convolutional neural network architecture. So at the top of the model, we must classify if there is a tumor present or not. To do so, we'll just output a single value using the sigmoid activation function, so the values of the output will cluster around 0 and 1, which will define if we think we have a tumor or no tumor. And then I also introduced some metrics to track as well during training, including precision, recall, AUC, and accuracy. So a couple of important metrics here. So precision is sort of like how many of our selective items are actually relevant. So how many images are we classifying as having a brain tumor when they like how many of them do in fact have a brain tumor. I think precision is a little less important than recall in the case of medicine, because recall is how many relevant items are selected. So if our model was not selecting all of the tumors, that would be cause for concern, especially since we would want to notify patients right away if they do have a tumor present in their MRI scan. So, but regardless, both precision and recall are a couple of important metrics to look at. Then here we'll take a look at the architecture of the simple model. So it starts with a convolutional layer with an output shape of 128 by 16. So 16 is the number of filters that we use in the first convolutional layer. Then we follow it with max pooling, batch normalization, and then we repeat with 2 extra convolutional blocks of the same pattern, flatten our data, and add a couple dense layers before our final output layer using the sigmoid activation function. Each one of these layers uses ReLU as the activation function. So this model did okay and achieved the maximum validation accuracy of around 80%, which is better than just flipping a coin, but let's see if we can do any better. And part of this issue is we don't quite have enough training data, but what will help us is taking advantage of transfer learning, so that's what I did next. I downloaded the weights for the Inception ResNet V2 uh, model, which was trained on the ImageNet database. Um, so we can simply import the weights, and we just take off the top of this model and then add two of our own dense layers to the top of the architecture. So then to improve the model, we can also allow for the weights of the last convolutional layer of the Inception ResNet to be altered during training, so they can actually be adjusted during gradient descent. And by doing this, the epoch with the highest performance on the training set recorded the following metrics. So precision of 1, which means that no images were selected as having a tumor if they did not have one. A recall of 96.968 or 96.8%. So very very impressive recall, considering that we already had a precision of 1. Our recall is pretty good as well, and then the overall accuracy of 98%. And then for those that are familiar with the AUC curve, we have a pretty good AUC, which is almost a combination of our precision and our recall, in a more complex way. But yeah, so just having a look at why the Inception ResNet was able to do so much better. It's a very deep network, and in between these big convolutional blocks, they did some cool techniques to prevent dead neurons, which is ReLU neurons that just only output 0. So if you want to have a better look at this architecture, I'm already pretty confused by it, but if you really break it down, it's this very deep network of a lot of parameters that were able to get us to our results, because it has such great weights for the image classification task that it was after. Taking off the top of the model and then having it perform a classification task of our own, we were able to create a very strong model right off the bat. So I wanted to see if I can improve this at all. So I imported yet another famous ImageNet architecture. So this architecture did pretty well, equal precision and recall, a maximum accuracy on the validation set of 92%, and yeah, so it did better than our baseline model, and with some more training, or perhaps some more data, I think both of these transfer learning models would do particularly well. So just as a summary, MRI scans are used for diagnostics in a lot of medical settings. So let's say that we want to identify if there's a tumor in the brain or not. We want to do this quickly and effectively, as opposed to waiting for a medical professional to interpret the scan. We can simply use a convolutional neural network to try and tackle this task. But with such limited data, we had to do things like introduce both image augmentations and transfer learning. But even with such limited data, transfer learning was able to produce a pretty highly performing model. Even at the worst epoch, the transfer learning model still scored above 84% as far as validation accuracy goes. So transfer learning really improved our performance. So some further considerations for seeing this model at scale, or perhaps a real use case, we would first need some more data to validate the performance of our model. Although we introduce image augmentation, we still need to expand our validation set, and maybe even introduce a test set, so that we understand how our model generalizes. And then perhaps a doctor would be sufficient in identifying if there's a tumor present in an MRI scan. There's no doubt about that, but things like different diseases might have different um, MRI scans, but their images may only vary slightly between different types of pneumonia, I think is one example. So another use case might be to classify more specific types of tumors or deformities within an organ or tissue. And now I just wanted to take the opportunity to go through just for 30 seconds or so what our code looks like. So we do all the necessary imports up here. If we go ahead and download from Kaggle, we can unarchive a zip file, and then all we have to do is drag the folders that say tumor or no tumor into a single data folder and create a directory structure that looks like this. Once we have this, we'll just use a plotting image function found on Stack Exchange, and then create our image data generators. So here we introduce a validation split. These are all of the potential augmentations we can make. And then we'll just do flow from directory. So when we select training, it knows to only take a subset of these for training. And then we'll do a validation set also using flow from directory. We'll take a look at the class indices just to make sure we're correctly defining them. So tumor is 1, no tumor is 0. And we'll have a look at some of the augmentations. So our first model is as described. So we see that the validation accuracy is all over the place, and we aren't reaching any sort of convergence here as far as accuracy goes. And similarly with loss, we start to stagnate a little bit. So to further improve our model, we have to introduce some transfer learning. Here we take off the top and take the ImageNet weights, define an input shape, and we go ahead and train a model using sequential with this base model, and then we just flatten and add our dense layers. So we see that the loss is significantly lower than our basic model, and it's stagnated around 0.25. And similarly with our accuracies, our validation accuracy is sort of bouncing around this 90% line, although it does achieve a maximum now. Oh, sorry, this is, I didn't allow for the convolutional layer to train yet. So after doing so, right here, then we see that we see this 98% accuracy, but we also see we start overfitting to the training set a little bit. Yeah, we achieve a pretty good accuracy by just allowing for the convolutional layer to train. Here's importing the other model, doing something similar, and the results here. So that is my project. Thank you for such a great summer course. This is I'm recording this from San Diego, California. I'm really happy that I had the opportunity to take a course of such high quality all the way across the country. So I'm glad that I was able to yeah, be a part of this. Thank you guys so much, and yeah, have a great rest of the summer.